So let's say we have this flat horizontal circle and it's going in uniform circular motion, which means that it has a constant speed v and a constant radius r. Okay, so we have this, it's spinning clockwise, and you know that at any point on this circle, the centripetal acceleration is going to, there's some acceleration vector, and it's always pointing inward towards the center of the circle, right? And so we know, we look at our equation sheet and we see that, oh, okay, I know how to calculate that. That is centripetal acceleration equals the speed, the linear speed of that object right there squared over the radius. Okay, but here's the problem. Maybe we don't know speed, right? If we don't know speed, you're kind of screwed when it comes to that because we wouldn't know enough to solve for this. So we're going to use some just kind of general substitution and using some other things that you might be able to get in a problem so that we can kind of work our way around this. So what this is going to use is general things that we know about a circle. So I know that the time it takes to make one full cycle around a circle is what I call the period. And that's we denote that with a capital T, right? That's some time in seconds. And then I also know that the distance around one full cycle, or the distance around one full circle, we usually call that the circumference, and that can be found with 2 pi times the radius, right? So why do we care about those two things? Well, if we don't know what the speed is, we can use our general just kind of knowledge with kinematics, and we know that speed is the same thing as distance over time, right? Well, distance around this whole circle is the circumference, so we could say that's 2 pi r. And the time for one full circle is what we call the period, right? So capital T. And using that little bit of knowledge right there, we can rearrange that equation and get it in terms of different variables that we might be able to have in a problem. So this is totally just a tool for you to be able to use depending on what you're given in a problem, right? So I have the centripetal acceleration is equal to speed squared over radius. Well, now we have this other thing that we can plug in there. So for the speed, I'm going to plug in 2 pi r over period, and that whole thing gets squared, and then I still have radius on the bottom. Okay, now it just takes a little bit of simplifying. So this squared squares everything inside of those parentheses. So the 2 gets squared, that becomes, here we can even go crazy, right? The 2 gets squared, the pi gets squared, the radius gets squared, right? The period on the denominator gets squared, and then all over radius on the bottom. Okay, so let's simplify this. This would basically be like 4 pi squared, radius squared, all over. The period goes down to the bottom, and then we still have that radius on the bottom. And you can see what happens. This little radius right there, is this going to be giant? Nope. Right, this radius cancels out with one of these up top, so that squared goes away. And overall, I would be left with this new type of version of centripetal acceleration, which is 4 pi squared r over period squared, right? This is totally something that you would use only if we don't know the speed, but maybe we know the radius and maybe we know the period, right? So this is, it's not on the formula sheet, but this is definitely just another way we can write centripetal acceleration just by substituting some stuff in that we know about kinematics. And that right there is a separate way that we can write the centripetal acceleration based on what you know. And we're going to use that in some problems that we're doing today. All right, so there you go.